I'm sharing with you today digital transformation, how that is impacted on the interlocking systems that we currently have and on the future. So, for those of you that are not aware, does anybody know what the function is of an interlocking? We've spoken quite a few times, thank you for the show of hands, on how safe the train system is, and that all basically depends on the interlocking system. So how does the interlocking do that? Well, it's actually very easy. All it does is make sure that no train moves into the space of another train, and that's the only way that it uses to prevent accidents from happening. So this space that I'm referring to, in signaling terms, it's called a block. And these blocks within station boundaries can be from a few hundred meters, or if you talk about between stations, these blocks can be up to kilometers long. So the interlocking then basically can be referred to as the brain of the signaling system. So today I'll be taking you a little bit through the history of interlockings, where interlockings come from, but also then where we expect interlockings to go, and then also how does that apply in South Africa. In terms of the history of interlocking systems, in the early 90s, you see there was mechanical interlockings, so these were huge mechanical infrastructure built next to the railway line, and this was used, the arm basically moving vertical 45 degrees, to show the trains or the train drivers whether they can proceed or not. So the limitation on this was because they were controlled with wires. You could only control signals from the station about 1.2 kilometers in each direction. These things were manufacturer independent, so basically anybody who understood the technology would be able to do this mechanical signaling. The section between the stations, these were controlled with a token, so in very simple principles, it was a bit disc that was given to the one driver, he would proceed to the next station. When he receives that disc, the next train is able to move into that section. So after this mechanical age came relay interlocking. Talk more about computers. Everybody knows that the first computer was mechanical or electromechanical, and this was basically the start of relay interlockings. So signals was then about 5 kilometers from stations, so we could more control signals further into the sections. We needed copper cable for this. It was very much manufacturer dependent. In South Africa there was quite a few initiatives between suppliers and Spoornet at the time to develop these kind of interlockings. And your section between stations was now controlled with very specific or specialized relays or block relays, and this could be done up to 20 kilometers. This was followed by electronic interlockings, which is maybe something more of you are familiar with. This is based on computers or PLCs or some specific hardware that's supplied by a supplier. Again, you still need copper cable for this into the sections. It's manufacturer dependent, so manufacturers would use very specific software, very specific hardware to run this type of interlocking on. And connection between stations are now on fiber. Everybody now knows with fiber coming to the home in Gauteng, what the advantages of that was. But now since then things have moved on, and the network age has arrived, and control distances are now almost unlimited. Everybody knows that when you've got a network, you can really expand it with any way, by fiber, by wireless. There's not really any limitations to that. Intelligent outdoor equipment is now possible. These, because of the way that the technology is, this is now not so much manufacturer dependent anymore, and your connection between stations could be now wired or basically on the network. So there is really not much limit on distance anymore. So what does this architecture look like? This network is now enabled a way to do an interlocking in the cloud, and this network system is basically now divided into 3 sections. So on that yellow disk at the bottom, what you see there is basically the stuff that you find next to the track, your point machines, signals, and then you also get stuff like axle counters or track circuits to determine the position of the train. These items will now connect through a public network or a customer network to a server cloud, which can be based anywhere. Maybe some considerations on where the server would be is dependent on the power grid network infrastructure or security considerations. And then on the third level, you will find your CPC or the train control system. And this system again would now be anywhere in the world. Again, more practically, we would probably want it in the country, but the same considerations really where the cloud server would be. Our vision is simple. On the previous slide, you would have seen at the bottom there on that yellow disk, there's a whole lot of infrastructure elements that we need to put down next to the railway line to control the train. So you've got point machines, you've got signals, you've got axle counters, and these are distributed along a whole line of thousands of kilometers if you look at South Africa. So our vision is simple. Safety logic in the cloud, and you only have point machines next to the track. These point machines are connected to a network via a wireless element controller. This wireless network could either be customer-based or it could be even on the public network. Unfortunately, there's one very important component missing on my drawing. I don't know who can tell me what that is.
The human.
Sorry?
The human.
The human? Alright, so unfortunately, we still need to deliver power to these point machines. Until we can find another way of delivering power to systems, we are still stuck with copper cables. So we are looking at developing a very high voltage DC bus that would be able to use small conductor sizes that is then able to deliver this power to the point machines. Load balancing through multiple feeds and use of buffers. When I talk buffers, it's basically things that can store power like capacitors or batteries that's able to handle the inrush current of these of the DC point machine. So what would the difference be? So practically, interlocking system would consist of 6 interlocking locations. These interlocking locations would be in buildings, basically like control rooms. You would have on-site module houses, which are houses distributed next to the railway line. You need cabinets, printed circuit boards to handle all these electronic devices, and all this would move into the cloud because you do not need all these things anymore when you've gone for cloud-based interlocking. The point machines, which are the things that switch the track, unfortunately, there's no ways of getting away from that yet. But we can also get rid of signals and axle counters through the use of ETCS systems. And then the big saving, and I think for South Africa, that's one of the biggest savings you'll have, and that's getting rid of the thousands of kilometers of cable that is needed to drive this traditional interlockings. Then we move on to the digital advantages that you can have because of these. So, because your interlocking system is now in the cloud, you are able to interface all other cloud applications like journey management, network planning, train scheduling, interfacing to other transport companies, and I'll get a little bit more to that, which brings me a little bit back to some of the earlier discussions also in terms of collaboration, but also any other cloud-based applications that can exist in the freight or in the moving of people environments. Then in terms of the digital processes, this cloud-based computer, because of all the information that you're able to gather, you wouldn't just have preventative maintenance, but you will now be able to have predictive maintenance, where you are able to predict when specific devices in your network is going to fail. You'll be able to have a global engineering team that is centralized or even distributed into hubs. And for South Africa, of course, in order to localize knowledge, the distributed hub would be a very big advantage. The testing of these interlockings is very specialized people required to do these tests, and with this system now being available in the cloud, you don't need specific hardware in any location. You basically test the system as long as you've got access to the internet. And all of this can be delivered to customers as a service. There can be contracts in terms of availability, and we believe it is possible to have a 100% available system. This can enhance passenger experience, maximum throughput, and like I said, guaranteed availability. So then in 2014, ULIX, now basically this is a collaboration between 14 different operators, was initiated to support the interfacing between different suppliers. Up to today, and many of your engineers in the room will know, the interface between suppliers is a big problem, but ULIX, this was created to really support the interfacing between suppliers, which will make it a lot easier for operators to bring in different suppliers and you're not tied down to use any specific company for that. So there on the right hand side you can see some of the companies that's involved with this. I don't know all of them, but I can see Deutsche Bahn and Network Rail as some of the operators that's involved. So just a few, this is what does it mean practically. So Siemens is currently doing a project with similar type technology. In the front here where you see a little box with a few components in, that's basically a distributed element controller, and these are the small boxes that you find next to the point machines that's now able to operate from the cloud. And this is not somewhere in the future. The second phase of this was commissioned in 2018, which is January this year. Then there's a few small projects again, also in Germany, in the center of Germany and the north. And I just showed this to show you the collaboration that takes place. So the interlocking is delivered by Siemens, but the outdoor facility is delivered by another company, S&B. And this is really because there is a central agreement in terms of how the interfaces work. Then on another project, the interlocking is delivered by Thales, while the outdoor facility with the element connectors is delivered by Siemens and S&B. Alright, so what is the future? When is this technology coming to South Africa? So I've done some, if you look at history, so mechanical interest signaling in the 1920s, relay interlocking in the 1960s, and then there was some sort of hybrid interlocking between PLC and relay interlocking in the 1990s. In 2010, around that region, electronic interlocking. So who can see the trend here? 40, 30, 20. So by 2020, somewhere there we should have cloud-based interlocking, maybe as a pilot only in South Africa. But what are the advantages of this? Why do we really want to push for this in South Africa? And I'm sure one of the topics that you have seen is the reduction in theft and vandalism. Until the economical situation in South Africa changes, we're going to have people who want to steal copper and sell it. And the big reduction in copper is one of the massive advantages of this. Increased reliability and availability, because your service provider is responsible and he gets paid on that, he will make sure your system is available. And then the initial investment cost, because you do not have a lot of buildings, a lot of cable and trenching to protect these cables, your initial investment cost will be a lot less.